curious, grounded tone. Out in the cold vacuum of deep space, a small machine is moving away from us at 17 kilometers per second. It has left the world that built it, and it is currently on a trajectory to outlive the stars themselves. When Voyager 1 launched in 1977, its objective was much more constrained. The original mission was to spend a few years photographing the outer planets. This orbital map shows a rare opportunity engineers recognized at the time. The outer planets were arranged in a specific curve that occurs only once every 175 years, allowing a single spacecraft to visit multiple worlds in one continuous arc. To make this work, Voyager relies on a physics technique called a gravity assist. As the spacecraft approaches a massive planet, it dives into the gravitational pull, steals a tiny fraction of the planet's orbital energy, and slingshots out much faster than it came in. By daisy-chaining these maneuvers, a short sprint through our local neighborhood accidentally generated the velocity required to escape the sun's gravity entirely. Voyager's first target was Jupiter. Up close, it revealed a planet defined by violent weather, dominated by the Great Red Spot, a churning storm 16,000 kilometers wide that could easily swallow Earth whole. But the biggest surprise was orbiting alongside the planet. As Voyager passed Jupiter's moon Io, it captured active volcanic eruptions, massive plumes of material shooting 100 kilometers into space on a world beyond our own. Moving on to Saturn, Voyager turned its cameras on the rings. What looked like a solid, pale band from Earth resolved into thousands of individual ringlets, entirely constructed from countless particles of water ice and dust. The final critical target was Titan, Saturn's largest moon. It is entirely wrapped in a dense, nitrogen-rich atmosphere, thick enough to completely hide the surface. To study that atmosphere, engineers flew the spacecraft exceptionally close. As it hooked underneath Titan, the moon's gravity bent Voyager's trajectory, throwing it sharply upward, off the flat plane where our planets orbit. That specific maneuver ejected Voyager from our solar system. The tour of the planets was over. The journey into deep space had begun. In 1990, Voyager turned its camera back toward the sun one last time, capturing the pale blue dot, a single pixel containing all of human history. After that, engineers shut the cameras down to conserve power. This diagram shows the heliopause. It is the boundary where the pressure from the sun's solar wind is finally overpowered by the interstellar medium. In 2012, Voyager crossed this invisible line, registering a sharp drop in solar particles and a spike in cosmic rays. By late 2026, the spacecraft will reach a distance of nearly 26 billion kilometers. At that range, it becomes the first human-made object exactly one light day away. A radio signal traveling at the speed of light takes a full 24 hours just to reach it. Meanwhile, its power supply is decaying. Voyager runs on radioisotope thermal electric generators, which slowly lose output over the decades. NASA has been systematically shutting down its remaining instruments one by one to keep the core systems alive. There won't be a dramatic mechanical failure. Eventually, the power will dip below the threshold needed to transmit. From our perspective on Earth, Voyager will simply stop answering. Long after we lose contact, the physical machine keeps coasting. In about 40,000 years, Voyager will pass relatively near Gliese 445, a star in the constellation Camelopardalis. No one on Earth will be tracking it. If we jump forward 3 to 4 billion years, the scale of the universe itself changes. The Andromeda Galaxy, our nearest large galactic neighbor, will loom larger and larger until it completely dominates the night sky. Andromeda and the Milky Way will eventually collide. The intense gravitational pull will reshape everything, merging the two massive structures into a single galaxy. Voyager will be somewhere inside that chaos, silently drifting along. 10 trillion years from now, the familiar era of the universe comes to an end. The massive, bright stars have exhausted their fuel. Only small red dwarfs remain, burning slowly in a sky that is steadily growing dark and quiet. If Voyager's metal hull is still intact, it will be older than nearly every star that once illuminated the Milky Way. Beyond the age of stars, we enter theoretical physics. One model suggests an event called proton decay. Over incredibly vast timescales, ordinary matter itself would gradually break down into lighter, dispersed particles. Under this model, the universe will ultimately erase Voyager. Time will pull its physical structure apart, atom by atom, until nothing is left. But bolted to the side of the spacecraft is an artifact built to withstand as much of eternity as physics allows, a gold-plated copper disc, known as the Voyager Golden Record. It holds audio greetings in dozens of languages, natural sounds of Earth, and music. It also contains an etched map using nearby pulsars, a set of mathematical instructions detailing exactly where to find our solar system. Long after its instruments fail, and billions of years after the world that launched it is gone, Voyager remains our ultimate monument. It is the physical proof that inside a vast cosmos, a fleeting civilization looked up, built a ship, and reached out into the dark.